All right, I will get started here.
Quick question.
Uh-huh.
I hit the top hat on my phone.
Oh, yeah, well, I don't know what to tell you. Except the top hat doesn't work half the time for half the people, so I'm not terribly surprised. Common solutions include opening Top Hat in the browser window on the phone rather than going through the app. Are you doing that, or? Yeah, that seems to usually fix it. But anyway, other questions before I get started?
When's our exam?
When is our exam? Oh, I don't remember. Before the end of class. I feel like it's after Thanksgiving, I think.
It is.
I think. I hesitate to speculate, but it's in the course planner, you know. So I don't remember off the top of my head.
It has to be after Thanksgiving.
I mean, we could have it Friday if you want.
No.
December 9th.
I got time to write a test. I mean, why not? Let's get nuts. Let's see, just a second, I'll tell you. So the first announcement I made in here, I attached something called a course planner to that. And if you look at that, it's got all the dates for everything in this term. So if I go to Canvas, and then I go to your course here, which is section 3, and then I look at announcements, and then I look at the first announcement that I made this semester, all the way down there. Welcome to Math 121.03. Attached to that announcement is a course planner. So that's the first announcement for this course. And that course planner tells you that test 3 is December 2nd, which is the Friday after Thanksgiving break. So we have quiz 3 the Monday after Thanksgiving break. Then Wednesday's questions for test 3, and then the test 3 is that Friday, December 2nd. Your final exam, if we trust my course planner, we should double check, of course, with the university schedule, but it's supposedly December 12th from 3:30 to 5:30 in this room. So, yep. Any questions? No. All right, well, I will begin with a word of prayer then. Dear Father, we thank you for this day. I thank you for these students. Just ask that you be glorified in what we do here this day, Lord. In your name I pray, Lord Jesus. Amen. All right, let me work an example here for you guys. So we did the half-life problem last time, right? So the half-life problem is, roughly speaking, I mean, it is almost literally, well, for me, it's literally number 4 from week 13 homework. Numbers 5 and 6 are pretty similar to number 4. Basically the same mathematics, so I'll let you work on those ones yourself. For today, I'll start with the Newton's law of cooling problem. So this is like number 7 from week 13 homework. All right, so here it is, and I mean it's also like section 4.6, number 27 from your textbook, for what it's worth. Yeah. Okay, so anyway, so in this problem, we're given that the temperature at time t is equal to initial temperature plus C times e to the minus kt, all right? And it tells you that C and K are constants, and that this T0 is the ambient temperature, or sometimes called room temperature, you know. Okay, anyway, so the situation is this for this problem. You've got a coffee cup, all right? And initially, the coffee is at, and F of t is the temperature of the coffee, okay? So initially, F of 0 is equal to 140 degrees. That's Fahrenheit, that's given, all right? So So the initial temperature of the coffee is 140 degrees. Okay? That coffee is put into a freezer. All right? So I draw a very sophisticated picture of the freezer. Here you go. There you go, freezer. And the freezer is at 0 degrees Fahrenheit, okay? And then basically what happens is you put the coffee cup in the freezer and then it cools off, right? It cools off according to the equation that's above, right? This is Newton's law of cooling. We're also told a few other things. We're given that, what else are we given? We're given that after 10 minutes, the temperature is 62 degrees. So we're at T equals to 10, coffee at 10 degrees Fahrenheit, all right? That's another bit of information we're given. And what else are we given? I said 10, I'm at 62. My bad, sorry. 62 degrees Fahrenheit. So here's the question. Use Newton's law of cooling to find the coffee's temperature after 15 minutes. So then the question is, what is coffee temperature after 15 minutes? All right, so there's my best attempt at writing the problem out here for you guys, okay? And this is like number 7 from your week 13 homework. Okay, so let's put it together. Let's take it bit by bit here. First of all, the ambient temperature we're told is what the T sub 0 is. Okay, so like what happens with this formula is as time goes to infinity, this piece dies off to 0. So after a long, long time, the temperature will be T naught, right? T naught will be the ambient. What's the ambient temperature for the coffee in the freezer? Well, eventually the coffee gets closer and closer to 0 degrees, right? So, in fact, the coffee will freeze, and at that point, this equation ceases being meaningful, and blah blah blah. So this is conceptually, it's an approximation that's good over a certain, degree of applicability. But so what we know here is that f of 0. Well, we know that T0, and basically the problem setup suggests this to you. T0 is 0 degrees Fahrenheit, okay, for this problem. So T0 is 0. So that means that we have f of t is what? C e to the minus kt. But what else do we know? We also know that at time 0, it's 140, right? So we also know that f of 0 is 140, right? But that's equal to c times e to the what? E to the 0, right? Which is what? E to the 0 is 1, so that's c. So therefore, c is equal to 140. Aha, so apparently f of t is actually equal to 140 e to the minus kt. So let me just recap here. I have used so far the fact that the freezer is 0 degrees Fahrenheit. I have used that the initial temperature of the coffee was 140 degrees, right? What have I not yet used? I have not yet used this information here, right? That at 10 minutes, the coffee's at 62 degrees Fahrenheit, right? So that's the next thing we need to use, see, because we're going to be able to figure out what that K is from that data. So what we have is f of 10 is given to be 62. And that's equal to 140 e to the minus 10k. Right, because t equals to 10 there. We want to know what k is, because if we know what k is, then that gives us a nice formula for the temperature at time t. So can you solve for k? What do you guys think? Can you solve this for k? What would you do? I'll do the first thing. I would do 162 over 140 equals e to the minus 10k. Then what could I do? Yeah, take the ln of both sides. That's the right idea. So if we take the natural log of 62 over 140, that's equal to minus, well, the natural log of e to the minus 10k, which of course is just equal to minus 10k. Now I solve for k. K is equal to, excuse me, k is equal to the natural log of 62 divided by 140 divided by minus 10. So what's k work out to? Well, I need my calculator for that, right? So let me get my calculator out. Hopefully I have it. Yeah. See what we get. Log of 62 divided by 140 and then divide by 10, I get 0.08145. I'll just keep that many digits. Okay? So now what? Well, now I can revisit the formula again, right? Now I know that in fact my f of t, the temperature of the coffee at time t, is equal to 140 e to the minus 0.08145 times time. Now, is that the answer? Well, that's not the answer, right? But it's one step closer, right? Now what? What was the whole question here? What were we asked? The question was, what is the temperature of the coffee after 15 minutes, right? So what's my last thing I need to do? I need to take that formula, right? And plug 15 into it. That should tell me the temperature. So f of 15 is equal to 140 times e to the minus 0.08145 times 15, and that should give me the temperature. So we just got to plug that into the calculator and work it out. Let's see here. So e to the minus 0.08145 times 15, and all of that times 140, I get 41.26 degrees. All right. And then what? What did the problem ask me for? It says round to the nearest integer as needed. So what would the answer be here? If I worked out to exactly 41.26, what's the nearest integer here? 41. So the answer is 41 degrees for my problem. It might be different for yours, but that's the idea. Any questions here? I mean, this one's a little bit more complicated than the half-life problem we did last time. Why is it more complicated? Well, Newton's law of cooling, it has the decay rate, the ambient temperature, and like the initial temperature. You need 3 bits of data to specify a Newton's law of cooling problem explicitly. For like the half-life problem, if you knew the initial amount and you knew the decay rate, that's enough. There's really only 2 parameters in the formula we looked at last time. And because of the way the question was asked, if you're just asking about half-life, you really only need, one bit of information, actually. Hey, an interesting follow-up question we could ask is this, right? Think about this. So we started at 140 degrees, right? And after 15 minutes, how much is it cooled? It looked like it cooled 99 degrees, right? So what if we wanted to say, okay, so how much more time do you think it's going to take to cool, say, another 30 degrees? What do you guys think? If it took 15 minutes for it to cool 100 degrees, right? If we wanted to cool like another 30 degrees, shouldn't it take like, what, 5 minutes maybe? Let's find out if we're right or wrong. How would we figure that out? We could look at how would we find what time it takes for the coffee to cool to 10 degrees Fahrenheit? How would we solve that? Plug in 10. We would not do that. We'd not just plug in 10. That's not what we do. Because think about it. We're looking for f of t equal to 10, right? Think about that. So we're trying to find what time will make the temperature be 10 degrees. So we can't just plug 10 in. We don't know what time it is, you see? So that's different. Logically, that's different than this one. See, because here we were, after 15 minutes, what's the temperature, right? So there you plug 15 in. But this is a different question, because the question is, what time is it when the temperature is 10 degrees? Well, we don't know what T that is, but we do know that the formula is this, right? So we just set 10 equals to 140 e to the minus 0.08145 times the time we don't know, right? Now you guessed it was another 5 minutes, right? So 5 plus 15 would be 20. Your guess is T equals to 20 does this, right? Let's see what happens. Solve for T. So we get what? E to the minus 0.08145 T equals to 10 over 140, right? Otherwise known as 1/14th. And so take the natural log of this, I get, minus 0.08145 T equals to the natural log of 1 over 14. And then solve for T, we get T, natural log of 1 over 14 divided by minus 0.08145. And let's see what T that gives us. Now this problem is not in your homework, but this is be a totally legitimate, like part B the homework problem could have had, right? A lot of times you'll find this question asked in this material. I get, 32.4. 32.4 minutes. So actually it takes an additional 17 minutes for it to cool 30 more degrees, roughly speaking. What does that mean? That means that the temperature loss is not linear, right? Like, in fact, the coffee is losing it's losing its temperature, like it's dropping from being very hot to being more lukewarm much faster than it is going, say, from being lukewarm to being cold. And this makes sense, right? Because the reason it makes sense is that Newton's law of cooling, what it says in its more like basic form, is that the rate of change of temperature is proportional to the difference between the temperature of the object and the room temperature. So the bigger the difference is in temperature between the object's temperature and the room temperature, the faster it cools. And that's what we're seeing here, is it takes a longer time for it to drop 30 degrees. It takes, in the same amount of time, roughly 15 minutes, right? It dropped only, 30 degrees to go from 15 minute mark to 32 minute mark. We dropped about 30 degrees, right? From the 0 minute mark to the 15 minute mark, we dropped 100 degrees. That's a much faster rate of dropping, right? So here's a practical application for you. If you like your coffee hot, right? Should you add the cream right after you make it, or should you wait to add it right before you drink it? Like, does it make sense to like keep the coffee hot to try to keep its hotness and then add the cream later, or should you add the cream right away?
Add it right away so you don't burn your mouth off.
Yeah, add it right away so you don't burn your mouth off, I think is a good answer. That is my way of being. That's true. But the other reason is that if you add the cream, you'd have to add the cream in at some point, right? And when you do that, the temperature drops, right? So if you drop the temperature by adding the cream in at the start, then the temperature of the coffee is not as removed from room temperature as it would be otherwise, which means that the coffee cools more slowly. So it's in your, if you want to keep the coffee hotter longer, you want to make it cooler faster at the start, which is kind of it sounds wrong if you just say it like that, but it's not wrong because Newton's law of cooling. But anyway, where was I? Oh, example 2. Any questions? Yes, no, maybe so. Let's see if I can find another word problem for us to chew on here today. Oh, see, this one's dangerous because I'm not sure I remember the formula for this one. You guys can help me out. How long will it take for an investment to triple if the investment is compounded continuously at 8%? if it is compounded continuously at 8%. All right. So you guys have a book for this class? Do you guys have a book?
Yes.
Where is it? Online? And you look at it?
Isn't it P like E and then RT is for continuous? I'm not sure.
So you say that the formula is P at time t is equal to
Oh no.
P naught e to the RT?
Yeah.
Yeah, I think you're right. Yeah, you're right. My point is that we could look in the book and find that formula, right? But since you remembered it, you'll save me 3 minutes of looking, so thank you. But you're right, that's the formula for continuously compounded interest. Now, we want to triple our investment, right? So if this 8% translates into what? R equals to 0.08, right? That's what that means in terms of the units we use here. And T is understood to be in time. That's understood to be a yearly rate, right? That's just default financial formulas. Now, we want to triple the investment, right? What's the initial investment? P of 0 is what? P at time 0, well, that's P0 e to the 0, right? Which is just equal to P0. So you see, this is the initial investment, right? P sub naught is the initial investment. So we're looking for the time when we get to triple that, right? So we need to solve what? What do we need to solve?
So we plug in the 0.8% for the R
Mm-hmm.
and then the time. It's unknown.
We don't know the time, yeah.
And triple, would that be like a 3
Mm-hmm. So you're saying we put 3P0 equal to what? Mm-hmm.
Would that be like 3, or would that just be 3?
Yeah, just P0 e to the R. Time we don't know yet, yeah? So
But we know the R, which is
exactly, we know the R, but we don't know the T, right? And actually, they don't tell us the principal, do they? Just like they didn't tell us the amount in the problem we worked last time. And it didn't matter because the amount canceled, right? The half-life is not, the half-life of like an atomic whatever, it doesn't depend on the amount that's there, right? Like the half-life of, say, an unstable isotope of uranium, it is what uranium, listen to me, uranium, it is what it is, right? Another one, like if you talk about neutrons, if you have a neutron that's just a free neutron floating out in space, those have a half-life of about 11 minutes. It doesn't matter whether you have one of them or if you've got 100 of them, the half-life is 11 minutes, right? After 11 minutes, about half of those neutrons will have changed to a proton and electron and something called an electron neutrino. That's just neutrons out in their lonesome, they're not stable. They're only stable inside like, the nucleus of an atom or something. So that idea last time, radioactive decay, is much like this in the sense that it doesn't matter what the actual investment is. See, the P naughts cancel, right? So whether you invest $100 or $1,000 or $1 million, if you could somehow get it invested at 8%, continuously, then the answer is it's going to take the same amount of time for that money to triple, whether you're putting $100 in or $1,000 in or $1 million in. It's the same deal, right? And in any of these scenarios, you're still losing money because inflation's like 11 or 12% right now. So, so don't invest. What should you do with your money? I don't know. Find a politician to bribe, I guess. That's the main thing. So 3 e to the RT. R is what? 0.08. I guess we're told not to make bribes. It's in the Bible somewhere, isn't it? Don't pervert the justice. So forth and so on. Just tempting. I don't know. So that's what you guys want me to do. Put the 0.08 in, right? And then we got to solve for T. How do we solve this? Natural log the thing, right? So take the natural log of both sides. We got natural log of 3 is equal to the natural log of e to the 0.08 t, which of course gives me back 0.08 t. So solve for t. We've got log of 3 divided by 0.08. Whatever that is, it is. Let's see what it is. How long does it take us to triple our money? Let's find out here. Exciting, right?
Any topic about years?
Yeah, years. 13.73 years. Fun fact, $1 in 1964 is now worth $25. That's how much inflation since like 64. I don't know, I ran into this some random place this week. I forget where it was, but anyway. Okay, so enough of that. Listen, there are a few more word problems like this. I think I've done enough in here that you guys should be able to work them. Like in number 9, so this one was number 8. This is, I think this might be the only one that doesn't have a formula for it. So probably this is the most important one for me to talk about in class because it doesn't come with a formula. Problem number 9, I think in problem number 10, they both have formulas. So you should be able to work the problem using the same principles we've already shown in the examples in class, right? Problem number 11, again, it has a formula. You can work it with the same principles that we've done so far. And so anyway, my larger point to you is if you want me to cover number 9, number 10, number 11, just ask me in a future class meeting, okay? And we can do that. I just want to go on to the other material because some of you will be gone Friday, right? Guessing. But I mean, I'll be here. We'll have class. But if you're not here, I understand plane rides, all that kind of stuff. I get it. It's okay. Just watch the video when you have a chance when you get back to where you can watch things. So, what's our next topic? Yeah? You guys remember? I don't know if I already told you in here or not, but our next topic is systems of equations. So what is a system of equations? And what do we mean by solving a system of equations? What's that about, you know? How do we do it, and how do we actually do it, right? How do we actually solve a system of equations? Now, before I actually show you how to solve a system of equations, what I want to show you to start with is just a geometric understanding of it in its most simple context. So most simple context of systems of equations is just when you have two equations and two unknowns. All right, so what is two equations and two unknowns? What's that look like? Right? That's the question I want to ask and answer. Oh, yes, it could, yeah, right, apples and oranges, or like you've got change, you're making it with quarters and nickels, right? The quarters and nickels could be like the X and the Y. So I don't know if we'll ever get back to those word problems, actually. We may just do the math for this part of the course. Hope you guys can forgive me if I don't give you word problems on systems. It's absolutely fine. Okay. So just symbolically, system of two equations something like this, yeah? ax plus by equals to c, and then dx plus ey equals to f. Here, a, b, c, d, e, and f are constants, right? They're constants, and here, so this is two equations in two unknowns. What are the unknowns? Okay. The two unknowns are x and y in my equation, right? And so what is it, how do you solve a system of two equations and two unknowns, right? So we can understand it graphically. Let's just take a look ahead what we're going to expect to see for two equations and two unknowns graphically. And so graphically, there really are three cases if you think about it. And so I'm going to draw xy coordinate system. I'm going to show you the three cases. All right, so we got a line, right? generically speaking, something like this, all right? See, because each one of these equations, right, what is it? What's the solution set to an equation like ax plus by equals to c? It's a line, right? You could solve for y if you want, y equals mx plus b, but maybe you can't, right? Maybe it's a vertical line. One of these equations could be like x equals to 3 or something, right? That's possible here, because I'm not insisting anything really. The only thing I'm insisting here is that these are constants and some non-zero, okay? Some non-zero. And what I mean by some non-zero, what I mean is I don't want to allow for A, B, and C all to be 0. Because if A, B, and C are all 0, that causes us problems. All right, so I am assuming that at least one of them on the left-hand side of these equations is non-zero. Otherwise, it's not an interesting equation for us. So, all right, genuine lines. So you have here's what it looks like, right? Just generically speaking, here it is. And what if I have another line? What does that generically speaking look like? What are the 3 possibilities? Schematically. You could have a line with a different slope, right? Like this. And in that case, that's what it looks like. What's the other possibility? I could have a line which doesn't intersect, right? Which is what? I could have a parallel line, right? No point of intersection. I tried to make them parallel. It never quite works out. And what's the other possibility that is kind of weirder? How about, what if the 2 lines aren't actually different? What if they're actually the same line? That's the other case, actually. The 2 equations are actually the same line. They may look a little bit different, but they're actually the same equation. So in each one of these, the point of intersection, if there is any, is the solution, right? So like case 1, let me call this case 1. There's a unique solution. There's a unique solution right here. In case 2, what can you say? No solution. There is no point which is simultaneously on both equations, right? And in case 3, there's infinitely many solutions. And it turns out, what happens for 2 equations and 2 unknowns, it's the same story if you talk about 3 equations and 3 unknowns, or just more equations, generally speaking. These are the things that can happen. Either there's a unique solution, there's no solution, or there's infinitely many. It's not possible to have a linear equation over like a real variable, where you just have like 2 solutions. Like what we've seen for quadratic formula, that can't happen for linear equations. At least not when we're working with real variables. Now, if we were working over interesting number systems, like things with different characteristic, like you might if you're a computer scientist, there are interesting things can happen. If you work with numbers that are built over something of a characteristic 2 field, then you could have like just 2 solutions or 4 solutions or 8 solutions or whatever. Anyway, so let's look at a couple examples here, and we'll figure out which one it is. All right, so example 3, I'll make these ones kind of easy, all right? These are going to be very silly examples, so they won't really require much effort on our part to solve them, all right? So first of all, suppose I have, x plus y equals to 1 and y equals to 2. That's a system of equations. It's a rather silly one because like my d was equal to 0 if you look at this, right? D is equal to 0. Do you guys see it? So if you just use your imagination, I've got the some of my C is 1, F is 2, A is 1, B is 1, D is 0, C is 1. All right, so what's the solution here? I just plug 2 up in here, right? And that gives me what? It gives me x plus 2 equals to 1, so x equals 2 minus 1, right? So my solution is minus 1 comma 2. So the solution is a pair. I'll draw a picture of the graph of this one in this little area right here. I'll make it small. What does this graph look like? So you've got y equals 1 minus x, right? Y equals 1 minus x. This is y equals 1 minus x, yeah? It's got a y-intercept of 1. It's got a slope of minus 1. It looks like that. Y equals 2. What's that look like? It's a horizontal line, yeah? Where is it? It's at 2, yeah? So y equals 2, something like this, yeah? Where do those lines cross? Yeah, they cross right here, which is the solution we found, namely minus 1 comma 2. So this is case 1. This is an example of case 1. And we didn't have to work that hard to find the point of intersection, did we? Because these equations were kind of silly. Let's look at another one. What if I have, x minus y equals to 0, x minus y equals to 1. So graphically, what's going on here? You've got y equals to x, and you've got y equals to, x minus 1. So graphically, what's that look like? Y equals x is this guy, right? And y equals minus x is, down x minus 1 down here, right? What's the solution? Right, so here, solution set is equal to the empty set. Or you could write it like this. In the previous problem, the solution set was what? It's a set that just contains one element, So the solution set up here, solution set is just a set containing minus 1 comma 2. All right, so example 5. So there is no solution, right? And how you could have seen that would, well, we'll talk more about that, but if you tried to substitute one of these equations into the other, you would have ended up with something like 0 equals to 1. And when you do that, you're like, oh, wait a minute, it's impossible, right? So no solution. Example 5, we could have something like this. Let's say, x plus y equals to 1, and 2x plus 2y equals to 2. See, on first glance, it looks like two genuine equations and two unknowns, but the truth of the matter is that second equation, what happens if you divide it by 2? It's the same as what? X plus y equals to 1, right? So these two equations, they're actually the same equation, right? That's the case that the two equations are actually, graphically the same line. What's the solution set here? All reals? Well, yeah, but we have, our solution set should be pairs. All right, so it's like x comma y such that what? X comma y such that x plus y equals to 1, right? But we can do better than that, because we could solve that for y, right? What's y equal to here? 1 minus x, right? And so you could rewrite this as like all pairs x comma 1 minus x, such that x is a real number. So anyway, the solution set in that case is infinite, because any point on that line is a point on that line, which means it's on a point on both lines, since both lines are the same line. That's what we're up against here, right? Those are the three cases. Do you guys know, have you ever heard the terminology consistent versus inconsistent? Do you know what that means? Can you tell me? As we look at cases 1, 2, and 3, which one of those cases is an inconsistent system of equations? Nope. Number 2, this is the inconsistent system. Inconsistent system is one which has no solutions. So only case 2 is inconsistent. Case 1 and case 3, these are consistent systems. It's just that this one has a unique solution and this one has infinitely many solutions, but they're both consistent. Consistent just means it has a solution, at least one. All right? I seem to have lost my phone. Did I bring it? Did I leave my phone up in my office or something stupid?
Is it under your towel?
No. Huh. I left my phone at home. No. Sorry, my kids are about to watch E.T. for a literature class. It's on my mind. Let's see here. I didn't get to watch E.T. for any literature class. What's that all about? You know, I didn't get to watch anything for my literature class, actually. It was just all boring. I would tell you what I would tell you what it was, but I don't even remember. It was that boring, you know. Okay, so listen, we didn't really need any technique to solve these, right? But we're going to need some kind of strategy for solving systems of equations going forward. So let's just try one and see if we can figure out a strategy. So example 6, suppose we're going to solve 2x minus 3y equals to 10 and x plus y equals to 4. How would you solve this system of equations? What strategy should we use? There are really, in my book, there are really 3 major strategies. The one is just to take both equations, get some graph paper, graph the line for each, and look for the point of intersection. That's a way you can solve it, right? If there's a point of intersection, you look at the graph where they cross, there's your solution, right? Done. That's actually pretty straightforward, right? But it's very, very tedious to do that carefully. Another good method is substitution, right? And that's what I'm going to do right now, substitution. So substitution is when we try to solve for one of the variables in terms of the other, and then we use that to plug into the other equation. So to make that systematic, let's call this equation 1. Let's call this equation 2. So we solve 2 for y equals to 4 minus x, yeah? You guys agree? Then substitute. Plug y equals to 4 minus x into 1 to obtain. What do we get? We get 2x minus 3 times the quantity 4 minus x equals to 10. So if we adopt this simple strategy of solve and substitute, we can solve these, right? It's just that simple. 2 equations, 2 unknowns. Pick one of them, solve for one of the variables, plug that into the other equation. You'll have 1 equation, 1 unknown, so you can solve it. This works every time. And so here we go. This is, but we still have to solve the equation, right? We have 2x minus 12 plus 3x equals to 10. So you got to isolate your x. This gives us 5x equals to 22, which gives us x is equal to 22 over 5. All right, that's half the battle. Now what's y equal to? We go back, right? You take that, and you go back up here, and plug it in there, right? So y equals to 4 minus 22 over 5, yeah? And let's see here. In terms of fifths, how many fifths is a 4? 20 fifths, right? So we have 20 minus 22 over 5, which I believe is minus 2 fifths. So there's your y. What's my solution? Solution is 22 fifths, comma, minus 2 fifths. That is the solution. And geometrically, that corresponds to the point. If you were to graph equation 1 and equation 2, right? The place where those two graphs intersect is that one. And I think this is actually pretty, I view this as a triumphant success of algebra because, you know, goodness gracious, to graph these two lines, that would have been a pain, right? That would have actually required us really doing some work to graph those two. But this is relatively easy what we just did, and we only had to do this much work to find the point of intersection, right? I mean, I think it's pretty nice, actually. Example 7. So the other technique we use to solve these is so-called adding equations. So suppose I've got something like x plus 2y equal to, I don't know, 5. And x minus 2y equals to, I don't know, minus 3. Solve these, right? So here, yeah, you could we can always use the solve and substitute method. But this one here, it's just easier to subtract equations. So subtracting equations is what it sounds like. Just draw a line here like this, put some parentheses like this, put a minus here like so. I mean, you don't have to put the parentheses, but maybe you do. I don't know. This is my idea, is I'm subtracting this, basically subtract the left-hand side from the left-hand side, subtract the right-hand side from the right-hand side. What happens is you get what? The x's be canceling. You get 2y minus a minus 2y, which is what? 4y, right? You get 4y equals to 5 minus a minus 3, which is, I believe it's 8, right? 5 minus a minus 3 is 8. So what's y equal to? Therefore, y is equal to 2. Hooray. And how about x? Well, x plus 2y is equal to x plus 4. And that's equal to 5, which tells me x is equal to what? X is equal to 1, right? Now we try, I mean, that's a perfectly good answer. X equals to 1, y equals to 2, right? Both of those things together is the answer. A better way to write the answer, thus, solution is 1, 2. What's the solution set? Solution set is the set containing 1, 2. It's obnoxious, but there it is. Solution set. The solution set is a set, after all. So, solve and substitute versus add equations. Now, there are other games you could play here, like example 6. We could have done this. We could have done like twice equation 2. Which would have given us 2x plus 2y equals to 8. And then we could have stacked that up against 2x minus 3y equals to 10, right? So we could have taken the second equation, multiplied by 2, then subtracted. See that? What would we have got? We've got, minus 5y equals to 2, which would have given me y equals 2, minus 2/5, which is what? It's exactly what we found the other way, right? So, but the thing is, this one wasn't nice for adding or subtracting equations unless you do what? Unless you take one of the equations and massage it a bit before you do the subtraction. Anyway, we'll talk more about this next class, and we'll also look at 3 equations and 3 unknowns, right? Because we need to do those too. But it's actually going to be more of the same. So, thanks, guys.